Well, hello, good morning, good afternoon, and good evening, ladies and gentlemen. I hope you can hear me all right. If you can just type in the message in the chat whether you can hear me all right and see me okay, that would be appreciated. So I'll get this presentation started. Again, good morning, good afternoon, good evening, ladies and gentlemen. It's a great honor to be presenting in front of you today. I would like to thank AAPG and EAGE for the opportunity to present. And my name is Jorge Costa Gomes. I'm from Portugal, and I'm doing my PhD at Heriot-Watt University under the supervision of Professor Sebastian Geiger and Professor Daniel Arnold. And my talk today is a hierarchical carbonate reservoir benchmarking case study for reservoir characterization, uncertainty quantification, and history matching. I can see some people can't hear me. I'm not too sure. I'm getting a mixed message here, but I'll continue. I must say that this platform doesn't allow me for the pointer, so just bear with me by telling you where I'm looking at on the slides. So the outline of my talk is to start off with the research objective, which has been to create a new open source carbonate reservoir benchmarking case study that accounts for geological uncertainties inherent to carbonate reservoirs. So I'll briefly talk about the existing open source reservoir models, and then I'll go into the uncertainties inherent to carbonate reservoirs and those uncertainties that we're tackling in the rebuilding of our geological models. With that in mind, we'll go straight into the geological construction of our truth case. So here I'm implementing the word truth case as an anchored philosophy or conceptualization of our base model. So we'll talk about the philosophy of the construction, the petrophysical data, the reservoir rock typing, the flow unit architectures, and the model initializations to complete all of the aspects of the geological modeling. And then from there, go into the reservoir simulation aspect of this work, which is all the inputs and the virtual drilling campaign that I designed in order to create our synthetic production data that will be also released for people to test history matching and optimization studies. And then to conclude, I'll talk about the model releases. So the research objective has been and continues to be to build an ensemble of realistic carbonate reservoir models with a hierarchy of uncertainty delivered in an open source format for benchmarking, upscaling, history matching, optimization, numerical method development exercises, and potential tutorials and senior design projects. Because if you're in academia, you're in industry, and you're looking to develop new numerical algorithms for reservoir characterization, reservoir simulation, optimization, what have you, you first need to have a subsurface type analog model to test your specific objective functions. And there's three ways to go about that. The first is to basically build your own geological model from scratch. And the second is to acquire a geological model already built by a company. However, these are really hard to come by because companies can spend upwards of millions of dollars developing these reservoir models. So if you were to acquire one, you would face confidentiality issues. So fortunately, there's the open source market, if I can call it that, which I'm showing you here on the right-hand side, a set example of open source reservoir models that institutes and professors alike have created for one to go and investigate. Here I'm highlighting some of the most famous ones like Punk S3, SPE10, Brucefield, Stanford 6, Wattfield, and Unisim 11. There's many more. However, all of the ones on the market currently are depicting of siliciclastic sediments, deltaic and coastal environments, meandering channels. The only initiative that looks into carbonate reservoirs as an open source was that as Unisim 11. However, out of everything that exists in the market, the only reservoir models that account for geological uncertainty is known as the Wattfield. So for the first time, you not only have an undisclosed truth case, but you have multiple geological versions of that, be it manipulation of the top structures, fault locations, petrophysical properties, and so forth. So the scope of my PhD is to do that into carbonates and then look into what are the unique uncertainties inherent to carbonates and go about that. So what are the uncertainties inherent to carbonates? So unlike siliciclastic sediments, as we know, carbonates are formed up of materials near or on site of final accumulation of that sediment. And what that means is that they're very heterogeneous entities due to early and pervasive diagenetic overprints on top of that. The growth of the carbonate factory is dependent on many things, but ultimately it's the static sea level rise and fall of a particular geological period. Depending on that, we'll start off here on the first column, first row, the depositional systems. You can have prograding catch-up carbonates, retrograding give-up carbonates, aggrading keep-up carbonates. And this is in third order, fourth order, and fifth order depositional cycles, okay? So one has to identify those in a hierarchical order. And then the associated depositional system would have a carbonate stacking pattern. So on the second row, I'm looking here, and this is for porosity trends, which works well in siliciclastic sediments. So if you have a prograding siliciclastic reservoir, you would associate that to have a coarsening upwards of porosity or a fining upwards of porosity in retrograding. But in carbonates, it's much more complicated than that. It's not associated with the grain sizes due to the diagenetic overprint. But nonetheless, you would have that association. And then your geometries, when you're building your stratigraphic framework, you would have prograding clinoforms, retrograding clinoforms, or just a typical layer cake type reservoir. So the first four rows are generally associated with one another, but then you also have the geological environment. Where does your carbonate fall in place? Is it the supertrital subca, platform margin, inner outer ramp? How are the facies continuous? Are they laterally extensive, laterally discontinuous, sigmodal? Do you have locified, karstified features? And then the generalized pore systems, carbonates are much more heterogeneous. You have multiple pore size distributions, intercrystalline, interparticle, you have diagenetic effects, cementation, leaching, dolomitization. And then the wettability of the formation is also an uncertainty. It varies with height above free water level, amongst many other things. And then ultimately the fractures. So fractures, many carbonates are highly fractured, but how is the presence? Is it major or minor? So these are the uncertainties, some of the large uncertainties in carbonate reservoir characterization. And the slides here, I'm just going to comment here. So to start off with, on the left-hand side, we'll start off with this truth case, this yellow box, which is for me to create this very high-resolution truth case depicting a carbonate reservoir formation that I'll talk about in the next slide, and then from there acquire a unique STOIP. From the STOIP, I can then produce this in a reservoir simulation model, sector of that, produce its rates, oil, water, and gas, and pressure. And then from there, in a y-axis and the x-axis, the y is carbonate reservoir uncertainties, and then the x is modeling scenarios. We'll start it in a hierarchical order of rebuilding with the same data set, multiple geological versions of interpretational uncertainties and modeling uncertainties, starting off with the stratigraphic framework, and then the reservoir rock typing techniques, the diagenetic overprints, and then the formation wettability, amongst many other things. But not only that, you also have the modeling uncertainties. So you can have your attributes, your approaches, your techniques, your drivers, and then of course your methods. So all of which has its own decision making to be done. So by the geomodeler and by myself by building this model. So where was I going to get inspired to build such a reservoir benchmarking case study? Because I wanted it to be inspired by real data and reservoir dynamics, but entirely synthetic, so that we could release this as an open source release. So having worked, lived, and studied in the United Arab Emirates for over 12 years, it felt appropriate that I continue studying the carbonate reservoirs of the region. On the left-hand side is an image of the oil fields in the Middle Eastern region, and highlighted in red is the area of interest, which is the United Arab Emirates. And here I'm focusing on the Bab Basin. The center image, and excuse me again, I don't have a pointer, so just please try to follow me here. The center image is a cross-section of the structural closures for a typical geological formation, here highlighted in red. And the same geological formation in this region can be found current day onshore and current day offshore. There's about a 3,000-foot difference in height between offshore and onshore for the same geological formation. And the philosophy was to see going from the platform to the interior, to the basin. So the philosophy was for me to try to convert the large-scale geological features of the region for a specific carbonate formation and try to structurally deform it in such a way to miniaturize the Bab Basin and also minimize the thickness variation between onshore and offshore to try to capture the large-scale geological features for reservoir simulation studies. But I'll get into more of that in the questions aspect. A lot can be discussed just on that alone. But let's have a look at what formations we're going to look at and tackle. So here is a lithostratigraphic scheme of the southern eastern Arabian plate. And two of the largest geological formations of the region, but also globally, are found here. Known here and highlighted in red is the Shuaiba Formation. It's known as a progradational parasequence. And underlying that is the Kharaib Member, which is an aggradational parasequence. And there's many things that can be taken from this diagram, beautiful work by Busham here, but there's basically three messages I want to get across. For the Shuaiba, the H1, look at the thickness variation from the platform wells to the basin wells. So there's a very large thickness variation. I can't zoom in the slide, sorry, sir. I don't have a pointer either. So the thickness variation from the platform to the basin, there's a very large thickness variation with these sigmodal type geometries, cliniform geometries dipping towards the northeast, and that's typical in the region. And underlying that is an aggradational parasequence, which has a more layer cake type reservoir architecture with very uniform thickness across the platform to basin, but also the facies are very continuous typically. If you compare that to this Shuaiba formations, the facies are very laterally extensively discontinuous from platform to basin. And these formations aren't only found in U.A.E, but they're also found in Qatar, Saudi Arabia, and Oman. So there's a huge interest for one to create a type of benchmark, a type of open source reservoir model that can capture these characteristics for people to run fluid flow simulations and reservoir characterizations. Let's imagine we're drilling the Shuaiba. So this is a really beautiful example of how heterogeneous it is and how complicated it is to characterize the stratigraphic framework and then the facies associations to start off with. So we can assume we have some wells, and the first step, of course, is to identify your sequence boundaries, your maximum flooding surfaces, lithostratigraphically, chronostratigraphically, what have you. And on the top left of the image, you see those dashed lines. It is quite continuous, so there is you can see that there's correlation within the well data, but on the right-hand side, it becomes quite discontinuous. And therefore, well correlation is not enough to identify these kind of carbon architectures that are found typical of this progradational parasequence. So a 3D seismic would be definitely used for better characterization and was used in this specific paper here by Lawrence. But nonetheless, the geologist and the geomodeler have to conceptualize an idea of what they believe the subsurface to be so that they can propagate their petrophysical properties and facies associations and link all of that to a believable story until you get something near to the truth. So the last image is the truth, which you have a beautiful example going all the way from the platform interior to the Bab Basin with multiple vertical and lateral heterogeneities. This is a third order depositional cycles here with multiple apartments. And as you can tell, a lot can go wrong going from well anchoring all the way to building your truth case. And the main message is that, as a famous quote goes, is that all models are wrong, but some are useful. So we should try to make as useful models as possible. And sometimes when we get stuck on one concept of the subsurface, all our modeling decisions go towards that. But what if you have a second conceptualized opinion? And you should then rebuild that. But we tend to just build one geological model and do all our field development plans on that. So it's different from multiple realizations. We're talking reservoir geological models here. So enough background about the region. We're going to go straight into my model, which I have created a miniaturized Bab Basin representation of the Upper Kharaib Member, starting off with the aggradational package. I use several wells from multiple fields in U.A.E. from different geodepositional positions and height above free water levels. The synthetic, I synthesized open hole logs and core data from publications, from many publications. There's over 200 publications on the fields around the region and the facies and diagenetic overprints. And all the data that I synthesized and acquired, I then had to make anomalous, rescale, reposition, structurally deformed, and the free water levels were normalized to place the entire model in a unique coordinate system, all in the effort to release this as an open source reservoir model in the future. So on the top left-hand side is a contour map, our synthetic contour map, because we didn't use seismic because of the nature of the exercise. We used well data from literature and we placed those wells in accordingly. So I have three main anticlines there, and I wanted to have the typical characteristics of the reservoirs from the shelf to platform in one, and a platform transition in the other, and then the transitional and basin sediments in the third and final anticline. That way we can try to encompass the reservoir characteristics at large from platform to basin. So on the right-hand side is the petrophysical properties, starting with our densities, our porosities, and our permeabilities across the three closures. And those that are familiar with the Upper Kharaib Member, you would know that there's a very typical association with permeability. There's about a 1 order of magnitude difference in permeability between the B upper and B lower, which is characterized there on the first anticline, the third anticline, where it creates quite a very field development challenge when you're producing or injecting water. Water tends to seep up to the topmost part of the reservoir, bypassing oil in the bottom. So we have been able to capture those kind of petrophysical property distributions. When we do reservoir simulation studies, one can then test field development optimization studies. One unique way that we did to model this reservoir was to model the pore throat size distribution. So top right is the Winland R35, going from a scale of 0 microns to 7 microns. By knowing your porosity, by knowing your permeability, you can compute your pore throat sizes and then distribute that in the reservoir. And for instance, on the top left of the first anticline, it's a more grain-supported limestone fabric with very large pore throat sizes, which is captured there in that light green. And the B lower is a more mud-supported limestone fabric with very small pore throat sizes. Therefore, this geological characteristics have been captured and was one of the ways we did our reservoir rock typing. So we have 27 reservoir rock types, and I'll get into why we have so many in the next slide. And then from there, I initialize the reservoir. So here is the true saturation, or our synthetic saturation distribution of the reservoir, showcasing very realistic flow saturation distributions with height above free water, multiple oil-water contacts, and very thick capillary transition zones. And thick capillary transition zones are very typical of this formation, creating very high water cuts for producers that are drilling through these transition zones. So this gives us a great challenge for reservoir simulation engineers to have a realistic fluid distribution of a reservoir to then look at multiple production and development scenarios as an undersaturated model currently. To build carbonate reservoir models and siliciclastics, it's extremely important to have special core analysis, because there you now start to look at dynamic behavior data, not only static data, but the way that data behaves dynamically in the sense of capillary pressure behaviors. How are the pore size distributed? Are they unimodal, bimodal, trimodal? So on the left here is our synthetic SCAL database. Starting from the top left is our oil brine capillary pressure curve, and it's the same data, just two different plots, just having different y-axis. And the reason for that is that the first one's at 120 psi and the second is at 40 psi cutoff. Our reservoir, my reservoir, has a maximum capillary pressure height, or a maximum hydrocarbon column, of 310 feet, which is equivalent to 40 psi capillary pressure. So that's why I'm looking at the data at the maximum capillary pressure height to give me a better understanding of how a particular rock type or PC curve would be saturated with height in my specific reservoir. Unfortunately, I don't have the pointer, but if you look at the cap curves in the 40 psi version, they show extremely high water saturation values, even at the topmost part. Whilst if you look at it at the wrong scale, you could be misinterpreted to think that that capillary pressure curve would have more oil and less water. So it's very important to look at those things. We also have bimodal, unimodal, and trimodal distributions to give us that realistic carbonate fabric characterization. And then our reservoir rock typing technique was to discretize those 500 capillary pressure curves into Winland groups, starting from 0 microns to 7 microns. And the increments are between 0.2 and sometimes 0.4. So let's say 0 to 0.2 microns, 0.2 to 0.4. And that's how we got our magical number of 27 rock types. For each rock type, there's a minimum of 3 capillary pressure curves to select. And that gives us real-life uncertainty in the selection of best representative PC curve per rock type. So when I specify I want to look at the data range of a particular pore throat size, I would select the best representative PC curve and the worst representative PC curve, and incorporate that as our reservoir rock types. What that allows us to do is to create an uncertainty in the STOIP. So now with the total of 86 capillary pressure curves, there's over 53 trillion model initialization scenarios. So if one wants to look at machine learning to figure out what was the secret combination that I've used, because I had to then select a secret combination of PC curve per rock type to create a unique stoip. But not only that, this also allows us to tackle the diagenetic uncertainties. So if I want to, for instance, manipulate a rock type to be more dolomitic, with reason, of course, or more cemented, I could, for instance, look here on the right figure rock type 12. I would select that green curve for a better performing rock type, or let's say a dolomitic rock type. I would select the green, and then I would select the purple curve, that's by the red, for a more cemented type rock type. Therefore, I can manipulate the way the diagenetic overprint is across the model. Now, you might ask me, why the curves look very sparse? I mean, they could be different rock types entirely. But if you look at it the right scale, so I'm looking at 40 psi still. If you go up to 200 psi, all those groups, they all group at one common irreducible water saturation. But when you're modeling thick capillary transition zones, it's extremely important to try to model at the maximum capillary pressure height of your reservoir, and even zooming in there. So when we get it, there's also uncertainties in the saturation height modeling. That is based on the reservoir rock typing technique and also the saturation height functions. And there's huge debate about which rock typing technique is best, capillary pressure driven, facies driven, or seismic driven even, or just a combination of everything, which is ultimately the best. But let's just imagine here in our truth case, we have our top left is our cross plot of porosity and permeability in 3D space in our static model. And then I have the 27 Winland R35 ranges from 0 microns to 7 microns. These are going to be my permeability transforms. And then I did a bivariant sequential Gaussian simulation of the permeability with respect to porosity, so it's honoring one another. And that was one of the rock typing techniques we initially taken. And then for each rock type, I had to derive a saturation height function. And there's many discussions about which technique to use or which methodology to use. I use the Scaled-Harrison to start off with, but you also have Tremere hyperboles, you have J functions, Omer functions, all of which can have give you different stoips, can also give you different matching with the curves. Some are better for unimodal, some are better for bimodal, and some are even designed for trimodal pore size distribution. So, but nonetheless, the way I can prove to you whether our rock typing technique so far and our saturation height functions have honored the data is to show you a series of wells here. So I'm showing you 1, 2, 3, 4, 5, 6, 8 wells. 8 wells with 3 tracks, the height above free water, the reservoir rock types, and then the continuous black line is the saturation of the log, and the upscaled cells of the saturation from our functions linked with our rock type. So we have captured very realistic saturation distributions at multiple heights in this reservoir. And also looking at, and when we characterize this, we have to look at the free water level. I mean, the definition of a free water, we have to have our MDT data. Of course, I don't have MDT data, and this is a synthetic reservoir. I try to be realistic as possible. But there is about a 30-foot uncertainty in the free water. So even if I shift that free water 30 feet up or 30 feet below, I still get a relatively good match with the saturation from the literature of a particular log. So we're incorporating the free water as a geological uncertainty. So enough about the geological modeling aspects. There's a lot of uncertainties there, a lot of decisions that have to be made, but it doesn't stop there. We also go into the reservoir simulation, and there's uncertainties there, geological uncertainties, the wettability, the saturation of the transition zone height, and then the irreducible water saturation and residual oil saturation after water flood. All these parameters and cutoffs that will define mobility of the fluids. So we initialize this. We're using a Blackwell conventional oil, a 3-phase oil, water, gas simulator with active hysteresis. So we have those 27 rock types. On the top left is 27 primary drainage capillary pressure curves. They're just cut off at their irreducible water saturations to make sure that they're in line with the constructed 27 relative permeability curves using Brooks-Corey, and then the 27 forced imbibition capillary pressure curves using Skleetland's equations. And everything is geologically consistent and made in such a way that the wettability profile that's showing you here in the USBM indices by integrating the areas above and below the set curves the way we've gone about the wettability, because we have the full envelope going from water wet to oil wet, is if you look on the top left curve, and I apologize again, I don't have the pointer, the capillary drainage curves. On the right-hand side, you see at least 4 or 5 capillary pressure curves that have irreducible waters of about 70 to 90%. And what that would mean is that you would associate that to very high microporosity. And if you would have high microporosity, you would assume statistically it would be more water wet. In vice versa, if the sample is, the capillary pressure curve has a very low irreducible water saturation, we imagine that to be more oil wet. So that's how we've gone about the wettability characteristics of our reservoir characterization. On the bottom, below the USBM curve, we have a cross plot of our irreducible water saturation versus our residual oil saturation after water flood. And this is a synthetic relationship, but nonetheless, it's still geologically consistent. The way the mobility of the rel-perm curves, the area above the forced imbibition and the area below the drainage, all of that is still geologically consistent. But there's many other inputs that we have to put in, the PVT, aquifers, and many more things that go into the reservoir simulation building. On the right, right below the flow unit architecture characteristics, I'm showing you that same cross-section of our reservoir, but highlighted in red is the first anticline, and we're targeting that to create our synthetic production data, and I'll get into why we're producing synthetic production data. But before then, let's just look right above there. There's 3 plots with the stratigraphic modified Lorentz plots. The red curve is the normalized cumulative flow capacity, and the blue curve is the normalized cumulative storage capacity. And for those of you that are working in the Middle East and you know the Kharaib member, you would definitely associate yourselves to these kind of flow unit architectures. So the first anticline, if you look, for the permeability, about 80% of the flow would occur in the topmost part of the reservoir and 20% in the base. But every anticline has its own unique flow unit architecture that we try to capture the generalized heterogeneities that are found in the region. But we're starting off with this first anticline to produce our synthetic production data. So here is, this slides, we're going to talk about the full field development plan. So the reason for producing this reservoir, so we constructed the reservoir and now we're trying to produce it dynamically to see how the oil and water rates and gas rates behave for a particular closure. And then by acquiring this production data with a realistic field development plan, like a virtual drilling campaign, we can then release that production data alongside with multiple geological versions of our truth case. And then a reservoir simulation engineer can try to history match our truth production with a case that is released. So here, for this specific anticline, it's 60 kilometers long and 26 kilometers wide. The flanks are dipping 0.6 degrees in the north and south and 1 degree in the western eastern regions. So it is steeper on the western eastern regions. I did not upscale this reservoir to the simulator, so it's still very high resolution. It's 15 geological zones subdivided into 62 layers. The layering is 0.6 feet to 8 feet thick, and the cells are all 250 by 250 meters long, so giving it a total of 1.7 million active grid blocks. And we're using an analytical aquifer using Carter Tracy, because if we were to use a numerical aquifer, there would be a large amount of cells. We could test that, but we just gone through an analytical one to start off with. Here is below that is the oil potential at the topmost layer, top layer 1 and layer 62, with the free water level highlighted in yellow. And the wells that you're seeing there are the 17 appraisal wells that were used to construct that geological closure. And what I'm about to show you now is the virtual drilling campaign that we've gone about, looking into the economics of the region. This is, we're assuming, is an onshore field development. And we're going to produce 206 producer wells, 84 infill water injectors, and 88 peripheral water injections over the span of 18 years. And we're going to go into that now. So the first 5 years, on the right-hand side where you see the oil rate, there's a little red arrow. So the first 5 years, we assume that period to be just a testing of the appraisal phase. We're producing 30,000 barrels. We're seeing how those wells that we used as appraisal, what do they tell us about the reservoir? And out of those 17 wells, 10 are in the oil producing zones and 7 are below or near the free water. From there, we have enough money to rent a rig or buy a rig or along those lines. So we have about 2 rigs starting in years 2025, drilling a 5-spot pattern. So we started off with a 5-spot pattern, but I have in the backup some different scenarios of what different production scenarios could look like. But because the reservoir is so large, we have 1 rig drilling 10 wells per year. Realistically, we could assume 10 wells a year with some mobilization, and then another rig drilling peripheral water injections all around the reservoir. And as we get through time, we're trying to capture and trying to drill across the best oil potential zones until in year 2030, here, we now get a 3rd rig drilling another 10 wells a year, so and so forth. So as you can see, as we get through time, we're trying to cover the whole spectrum, the whole reservoir. And here, this is how it looks like in real life. Our depth structure map with the full field development plan for 18 years. Top structure map here. On the right is the oil rates. So I'm looking at the oil rate plots here, and the blue curves, the solid line blue curves, is a case where I'm just allowing the rates of the oil producing wells to be at 5,000 barrels a day and to produce no less than 300 psi above the bubble point. So it's a very conservative plan, 300 psi above the bubble point, just to be on the conservative side. But then I also ran 3 different and actually more oil plateau scenarios. So the red, the green, and the purple, where I'm now trying to stabilize the plateau by with the simulator trying to choke back wells and manipulating their performance in such a way to try to flatten that curve out. And then we're going to select one of those cases as our truth case. Of course, we also have our water injections. What's interesting is only after the year 2040, after the first 20 years, does the voidage replacement start to be close to 1, and it goes above that in year 2025, in years 15. The total amount of oil produced in the first 15 years was 1.6 billion barrels. So that's 10% recovery factor, which means that this reservoir sector has a potential of 16 billion barrels of oil, making it one of the top 50 largest carbonate reservoir examples for one to test and do their full field development plans and optimization studies. So I'm running out of time here. This is my last slide. Just to conclude, I'll touch upon the model releases and outcome again, which was the deliverables is multiple geological versions of the truth case will be released, accounting for a large range of hierarchical, geological, interpretational, and modeling uncertainties. The logs that I used to construct the reservoir will be part of the release data, so you can go ahead and rebuild your own geological models if you wish to do so. Along with that, we'll have over 200 references, so paper numbers one can look at, and the synthetic production data that we have synthesized will be used for history matching. So as I had mentioned, we provide you the production data from our truth case, but we undisclose that truth case, but we then provide you multiple geological versions, and you can then test the behavior of one geological uncertainty on the production data, for instance. The SCAL database, the 86 cap curves will be provided, and this is all planned in Q4 2020. And this, in the center, these images are examples of different geological versions. For instance, starting with the rock types, how many rock types is enough? Some people use 1, some people use 2. Here I'm showcasing the first is 3, then 5, 7, and then the full-blown 27 rock types for that one closure. If I produce the 27 rock types, will I get a good match from a model that only has 3 or 5? These are all questions that can be taken into understanding. But we wanted to go with the very high detailed problem and then downscale from there. Of course, then you also have your porosity permeability distributions. And here I'm just showing you the Winland, but you also have Lucia, GHE, transforms, rock typing techniques, showcasing those different levels of heterogeneity. And then the free water level, as I mentioned, there's a 30-foot uncertainty there. So we have 3 different cases. And for instance, if you're a reservoir simulation engineer and I provide you the production data of one of these cases, but then give you a model with a different free water, what are you going to do? You're probably going to think, oh, I'm producing less than the amount that he's given me, so I might have to tweak porosity values or so forth. So and then the stratigraphic framework. I've currently built 2 ensembles. So I've looked at I've interpreted the subsurface slightly differently, making zones slightly thicker or thinner, changing the tops up or down. The baffles, for instance, we have 8 baffles, and are they continuously, how is the anisotropy of their petrophysical properties? I can manipulate that. And then there's many more different geological scenarios. So without further ado, I'd like to thank you all for your attention. And these are the publications of my PhD so far. So you're most welcome to go ahead and read more about my work. The first 2, unfortunately, have been postponed due to COVID-19, but I'm very active on ResearchGate, so you're more than welcome to use that. So thank you so much. I'll answer some questions.